just.
Okay, you good.
An hour of class.
Okay, so an oscillating system for which the net restoring force is proportional to the negative of the displacement is said to exhibit simple harmonic motion. An oscillating system for which the net restoring force is proportional to the negative of the displacement is said to be simple harmonic motion.
What does that mean?
Okay? You know the net restoring force, right? Equals negative kx. Okay? This is the displacement, right?
Yeah.
And this is the negative of the displacement. So all it's saying is, if I have my equilibrium here, and I've got a starting point here, but I displace it a certain amount and it moves back and forth, its net restoring force is going to be equal to negative kx. The greater the displacement, 1, 2, 3, 4, the greater the displacement, the greater the force, right? Okay? If I have a system like that, it will keep bouncing back and forth forever in this way, and we call it simple harmonic motion. Okay? So any system that has that kind of a vibration that's characterized by this restoring force is given the name simple harmonic motion. Okay? And the system can be called a simple harmonic oscillator. Most solids stretch or compress according to Hooke's law, so most vibrations set up in solid materials can be viewed as simple harmonic vibrations. So when I knock on the door, it sets up a simple harmonic vibration in the door, and we hear that as a sound wave because it vibrates our eardrum at the right wavelength. Okay, so pretty much anything will vibrate. Okay, now the thing that's a little uncomfortable to us about it is that it stops vibrating, right? Okay, we're saying that our model is a system that doesn't stop vibrating, but most things that we see in life, real life around us, do stop vibrating after a very short period of time because there's a lot of tension within that material as well. It can vibrate, and we can see that it vibrates because we hear the sound, but it doesn't vibrate very long because, as you guys dealt with in ATAM, there's hysteresis. Okay?
What?
Hysteresis, that's the property of it being dampened.
Oh, damper. Okay.
Okay? Any force that is restorative, indicated by a negative sign, and is proportional to the displacement of the material, will set up a vibration in the material. So, what is it that when I pound on this and I cause it to be displaced from its equilibrium, what is it that restores it back to its original location? And we can't even see it vibrate, right? But we know that it does because we hear the sound. But when I vibrate it, I do displace it from its original position. What brings it back to its original location?
The restoring force.
But what's causing the restoring force?
The KX.
The what?
Structure of the building.
Yeah, the material itself, right? The elastic properties of the material itself bring it back to equilibrium. Because what did we do to it with the energy that we applied? We stored potential energy in the elastic properties of it, and when it came back to its equilibrium point, that potential energy was returned as
Kinetic. Sorry.
kinetic energy. Thank you. Okay? And it vibrated a few times, but its elastic properties were overcome by the dampening properties of the material, and it slowed down and stopped. But notice how all of this fits together. I give it energy, right? I apply mechanical energy to it, and that causes it to be displaced, and that mechanical energy is stored as potential energy for the briefest of times, and then it's returned as kinetic energy to that equilibrium point and a little bit past, and it keeps doing that for a short time until all of that energy is drained away. And the amount of energy that I apply to it, hopefully you understand, could be related to the amount of potential energy that it stored initially, and then if I knew how much energy was lost each time, I could figure out how far it was going to move, because I know that potential energy is going to be converted back and forth into kinetic energy, and then back to potential energy and into kinetic energy. So we can start from that basis to think about how we're going to analyze the motion of this that we're talking about. Okay? It should make sense that we might want to quantify this motion mathematically and relate this motion to the amount of force causing the motion. Okay? What do I notice if I hit it harder?
Hurts more.
It hurts more, yes, okay? But I get a greater vibration, right? I get a greater amplitude. Okay? There should be some way I can relate this motion, this back and forth motion, to the amount of force that I used causing that motion. And it should also be related to the amount of any restoring force provided by the material, right? If I used a certain amount of force, or I did a certain amount of what? Work. If I did a certain amount of work, I would expect that amount of work back. Okay? Or however much energy got sucked away from it by the tense nature of the bore, but the amount of any restoring force provided by the material should be related to the amount of work I did on it. Okay? So, because forces vary depending on where in the cycle the oscillation is, it's difficult to analyze the effect oscillating forces have on motion over time. We've already had this problem once when we tried to figure out how much potential energy we stored when we did a certain amount of work. How much potential energy do we decide that a certain amount of work does to store energy in a spring? What was our formula for that? 1/2 kx squared, right? But we had to go through this whole process of thinking, well, if the force equals kx, okay, and I know that that's going to have to be multiplied by the distance. Remember, force times distance, and this is already x, and this is kx, but it's not the same force at the beginning as it is at the end, right? Okay, so we had to take the average force, and we decided that the average force was 1/2 kx, so the amount of work ended up being 1/2 kx squared, which is the amount of potential energy we store. Forces vary depending on where in the cycle the oscillation is. And we've already shown that. At this point it's the strongest, at this point it's a little bit weaker, at this point it's a little bit weaker, at this point it's a little bit weaker, at this point it's 0, and then it goes the other way. So that, without calculus, provides some difficulties for us in an algebra-based class. Those of you that know calculus a little bit or a lot would have an easier time figuring out how to deal with this. Okay? So force is always changing. So where do we begin our analysis? Here's the force, 20 newtons, 10 newtons, 0 newtons, -10, -20. Where do we begin our analysis in order to figure this out? So let's see if we can do this. Work is done to stretch or compress a spring. Let's review what we said about this in the chapter on work and energy. A useful approach is conservation of energy. Work is done to stretch or compress. Did I do something weird with the notes there? Did I miss something?
No, that's how it goes. A1.
Okay, so we know that potential energy is stored in an elastic substance. If we want to calculate the amount of potential energy available to do work for a given spring, we would correctly assume we need to calculate the amount of work required to accomplish that, and we already did that. Remember, we just couldn't use F times D. The greater the stretching, the greater the force, but the variation is linear, so we can just find the average force and multiply that times the distance. And then we said we could also simplify things by starting from the point where the spring is relaxed. That means one of the forces we use to calculate our average is 0, while the other force the spring is applying is at the distance to which it is stretched. And we ended up saying that our average force was 1/2 times 0 plus kx equals 1/2 kx. So that's how you would go through the full proof of that. And then we use this in our work formula, and we get that the potential energy is 1/2 kx squared. Okay? So, one of the things that we know is that the total mechanical energy is the sum of the potential and the kinetic energies. And we use that in solving problems like skiers at the top of a hill down to the bottom of a hill, right? We said our kinetic energy plus our potential energy in the final situation had to equal our kinetic energy plus the potential energy in the initial situation. So we know that the total mechanical energy of a system is the sum of its potential energy and its kinetic energy. Well, in this case, we're not talking about gravitational potential energy, we're talking about elastic potential energy. So, 1/2 mv squared plus 1/2 kx squared. V is the velocity of mass m at a distance x from the equilibrium position. So if I have an equilibrium position here, and I've got distances yes, I know that it's not exact. That's going to bug me though. Okay, so at some point, there's going to be a velocity right here, okay? So V is the mass of the velocity m at a distance x from the equilibrium, and that we would say is -3. We assume friction is negligible. Kinetic and potential energy are constantly exchanged as the oscillation occurs. Can you see that? If I'm here, I've got a certain amount of potential and kinetic energy, but that's going to be different from here, and that's going to be different from here, and that's going to be different from here, and so on. And they're just going to sit there going back and forth like this, right? Okay? Potential energy and kinetic energy are going to keep going back and forth like that. Okay? At extreme points, whether compressed or stretched, A and negative A, energy is stored completely as potential energy. Okay? This is not a whole lot different than what we did with the skier on the slope, right? At the top of the slope, if the skier didn't start with any movement at all, if they started from rest, their potential energy was 0. I'm sorry, they're kinetic